the time graph. Let's go.
10 seconds.
Okay, so we were talking about dimension. So I said that we wanted to study dimension via finite morphisms. I haven't told you what these are. This will be the next thing I tell you. But these are in particular morphisms whose fibers are finite, so they're finite to 1, and but they're a little bit more restrictive than that. And so let me try to introduce finite morphisms. First, I talk about so. Let's see. Let's tell you what it is. So first I say it in a rough way. So a finite morphism so I actually only need it for defined varieties. So of defined varieties is a morphism. So x and y. Phi from x to y, such that now these are defined varieties, so such that E of x is a finite phi star of AY algebra. So this, so first, remember that if I have a morphism phi between defined varieties, we get a homomorphism, the pullback phi star from AY to AX, and so in particular phi star of AY will be a sub K algebra of AX, and we want this to be AX to be finite over it. I haven't told you what that means. So the next statement, the next question is, in order to make sense of this definition, we have to know what it means for a K algebra to be finite over another K algebra. So that's the next statement. So to make sense of this, we have to define. The finite K algebra over another K algebra is. So let's see how that goes. So I now define that first, definition. So we assume that we have two K algebras, one contained in the other. So A should be a subring of B. Okay. So for B1 to Bn, some elements in the bigger algebra we call, so denote, so I call this A of B1 to Bn. So this would be just all the biggest kind of sub-algebra of B, which contains B1 to Bn. So this is the set of all G of B1 to Bn, where G is a polynomial. Okay, so everything we can write as a, this is K or N. Yeah, that's okay. So in B, okay, so we write any polynomial expression. Do I want a K or A? I think I want A. Yeah, that's better. Okay, so we can write any polynomial with coefficients in A, put this BI into it, everything we can get in this way is we have here. So this thing is called so the A algebra generated by B1 and Bn.
Actually, this is ambiguous.
What?
Sorry. Sorry.
So the question has resolved. Okay. So this is this A algebra generated by this. Okay, so this is just one thing. This is not what we're really looking at here, but we will need this in the future. But now, what does it mean, this thing with the finite? So we say that B is finite over A if we can write, if there exist now finitely many elements, well, maybe I can make both definitions then as we're there. So first we say B is finitely generated if there exist finitely many elements, say B1 to Bn in B, such that B can be obtained as the A alpha generated by it. So this can be reasonably big. For instance, you see that the polynomial ring in variables over a field would be a finitely generated K algebra. In fact, we know that AX for any for any affine variety will be a finitely generated K algebra. But what we're interested here is we see that B is finite over A if something much stronger holds, namely if there exist finitely many elements see again B1 to Bn in B, such that we can write every element in B as a linear combination of them. So I could write such that B is equal to A B1 plus Bn. So that means just every element in B can be written as a linear combination sum AI Bi with the A index. So this definition is set of what sum I equals 1 to n AI Bi with A I in A. Okay, so you see that's a big difference whether you can write it as a polynomial in the Bi or whether you can write it as a linear combination. For instance, if A is equal to K, then B being finite over K as a would mean, as a K algebra would mean it's a finite dimensional vector space, and on the other hand, any polynomial ring will be finitely generated. So this is this definition.
But there is a problem here in this definition now, that we are assuming that the map is injective. Because
No, I'm not assuming that here. That
No,
it's
but because this definition we need.
no, I say it should be a finite phi upper star of AY algebra. It's a finite over the image of the pullback.
Yes, but this implicitly assumes that the map from AY to AX is injective because
No.
we need that the two
No,
K algebras.
Yeah, but the algebra over which it is supposed to be finite is this, the image.
Ah.
It's not AY. Okay?
Sorry.
And so in that sense, we don't need inject. Yeah. Because we had otherwise there would be this would pose a restriction because we had this homework that this would say that the image is dense, and we'd see under our assumptions actually would imply that the map is surjective. In general, it isn't, but for finite maps it would. Okay. So. Now, we can explain this in other ways. It is related to the concept of modules over ring. Let me just say that so that we should go with us definition. So we can explain this in terms of modules. So, R should be a ring. And so an abelian group M together with an operation so which I call scalar multiplication from R times M to M. So, which just means that R M to R times M, or I also drop the multiplication, is called an so if I have this, is called an R module. Remember that for us a ring is always commutative with 1. So if we have the following actions, so if for all R, R1, R2, and R, for all M, M1, M2, and M, we have the following. First, that we have associativity of the operation okay. This associativity of the operation, so it's an actual operation. The second is that distributive laws, so we can take R multiplied with the sum of the elements in the module. This is R M1 plus R M2. And also we can take the sum in R in the ring, so R1 plus R2 times M equal to R1 M plus R2 M. And the third one is just that if I take the identical element in the ring and multiply it by M, this is M, as it is. So these are actually the same axioms as the axioms of a vector space over a field. So it's just the total analog of a vector space, where just in case we are not over a field but over a ring. Okay. So an R module B is called finitely generated if, well, the same thing as before, if there are finitely many elements B1 to Bn in B such that every element in B can be written as a linear combination with coefficients in R. I said, if R is a field, this just says that B is a finite dimensional K vector space. And so, obviously, we see from our definition that oh no, we are not yet there. Let me give some examples. So first I want to give some examples of R modules. So first, an ideal. So if R is a ring, I in R an ideal, then it follows that I is an R module. Just via the normal multiplication in the ring. So we have the scalar multiplication R times I. So I, because we know if we take any element in I and multiply it with an element in R, we end up in I. And the axioms here are trivially follow directly from the actions of the ring. In the same way, still if I is an ideal, so still I in R an ideal, then we can put then if I take A equal to R mod I, so the quotient ring, this is also a module. So just via if I have an element in A and I multiply it with a class modulo I of some element A in R, then this is just defined to be R times A in the class of that. And this will again trivially satisfy these actions because we are in a ring and the quotient is also a ring. And then, I should maybe say, okay. And then finally, so if A is a subring of a ring B, then B is also an A module. Just via the multiplication in B. No? Restrict multiplication in B. So A times B. So the multiplication in B is a map from B times B to B. I can restrict it to there, then obviously it gives us a module structure. Okay. And note we see, if now our rings happen to be K algebras, we get modules, and if we get that we look at K algebras, and the K algebra will be finite over another K algebra if and only if it is finite, a finitely generated module. So, if A and maybe B are K algebras, then obviously by this B is an A module, and B is finite over A. If and only if B is finitely generated as an A module. Okay, this is just because the definition is the same. No? we have just said finally generated just means this, and it's the same definition that we have defined. But here we are assuming we're talking about algebras and not just modules, so we have this additional modification. Okay, so now I want to prove some first properties. So how some kind of, where there's some kind of transitivity, so if something is finite over something else, and that is finite over something else, then the first is finite over the last, and some further statements of similar kind. So let me write this proposition. So this actually is the most trivial part, some more interesting. So let A contain B contain C, the K algebras. So if B is finite over A and C is finite over A, well then C is finite over A. And conversely, if C, I mean partially conversely, if C is finite over A, I can never remember which one of the two is, then C is finite over B.
Even if C is finite over B.
What?
The first condition, sir. C is finite over B. If P is finite over A and C is finite over B.
Yeah, but certainly, yes, that's a misprint. Thanks. Yeah, that's obviously that's the logic of how we want it. And here I say that if this is finite over this, then at least in this step it's fine. So, okay, the second statement is more interesting. So, let B A finite A algebra, and I also assume that B is an integral domain. So without zero divisors, then every element x in B satisfies a monic equation over A. So what I mean is, it's an equation of the form x to the n plus a n minus 1 x to the n minus 1 plus and so on plus a0 is equal to 0 for some n and a n minus 1 until a0. So the important thing is it's not just a polynomial equation, but the leading coefficient is 1. No, we can normalize the leading coefficient to be 1. So as we are here in a ring, we cannot necessarily divide by the leading coefficient. And there is some converse to it. Some converse. So conversely, if B in B satisfies the monic equation over A, then if I take AB, so I take the A algebra generated by B, it's finite over B. Okay. So 1 and 3 are essentially trivial, but we still have to do it. And 2 is a little bit more interesting, but we will do it all. So, proof. So we assume, so first here this thing, so assume, so if B is equal to A B1 plus A Bn, say, with Bi and B, and C is equal to B C1 until C B Cn. So this was Bi elements in B and Ci, so this was maybe N. Ci are elements in C. Then obviously, so that means you can write any element in B as a linear combination of these, of the Bi, every C and C as a linear combination of the Ci with coefficient in B. Then it follows obviously that we can combine this, namely C is equal to the sum I equals 0, 1, N J equals 0, 1, to M A times Bi Cj. No? Because each element here we can write it, so you can write these as linear combination of the Ci, with the coefficient you can write as linear combinations of the Bi. Okay, so this is the first step, and the other one is even simpler. So if C is equal to the sum I equals 1 and A times Ci in C, then obviously C is also equal to the sum I equals 1 and B times Ci, because A is contained in B. So I can just take the same linear combination as before, and that satisfies our condition. So now we come to the part 2. And for this we want to use the determinant. So, I mean, you can see, if you look at it, here we actually have to find this, we have to actually find this equation. It must come from somewhere. It doesn't really look like there's any reason why there should be such an equation. And we get this equation from looking at the determinant of something. We show that a certain thing is linear dependent, and then the determinant of something must be 0. And that this equation is this equation. And in order for this to make sense, we need to have coefficients in the field, and for this we use that B is an integral domain, so we can work over the fraction field. Okay, so that's good. Use the determinant. So first I do it in general, so let R be a ring. And D equal to, say, Dij, I and J going from 1 to N, the matrix. In R. So then the determinant of this D is defined to be, and we had this in the thing, so that would be the sum, and there are several ways how you can do it. Anyway, it would be the sum over all sigma in the symmetric group in n letters. And we have the sign of this permutation times the corresponding product, D1 sigma 1 times Dn sigma 1. Oh, this is how the determinant is. One of the ways how you can determine, define the determinant, just by the simplicity formula. And this will be some element in R. Now assume, so if R is contained in another ring C, and we take some element X in C, then we can look at the determinant of X times the identity matrix, so X times, I'll write it here, X times delta J minus Dij. So I could first write like this, X times the identity minus D, where X is the n times n identity matrix, and D is as before, or if you want, this is the determinant of X times delta Ij, so is 1 if I is equal to j, 2 otherwise minus Dij, and this matrix I j 1. And so what can we say about this qualitatively? So it will now, so this Dij are in R. The only thing which is not in R is this X. So I claim we can write this as X to the n plus sum I equals 0, n minus 1, ai, x to the I, where the ai are elements in R. How's that? We just have to see, at the most, we can, the only way how we can get x to the n is if we just take here of this thing the diagonal term and only the part with the, and then of that only take the part with x. No? So if you take this whole sum, there's only one where all the terms are diagonal, and this will be x minus d11 times x minus d22 and so on. So this is, if you multiply this out, this is already of this form. And all the other terms that you take here contain less terms on the diagonal. So if I sum it all up, I get something of this form. No? Okay. So we have this. So this is a monic polynomial in X. So that's kind of. So now let's look at our assumption. So assume that our B is equal to sum I equals 1 to n a times bi. So B is finite over A. And we take some element x in B. You have to find a monic equation for it. So clearly, if we take x times bi, this is also an element in B. So it must be, we must be able to write it as an accumulation of these. So this is of the form can be written as sum j aij times bj, for sum aij in A. No, because this lies in B. And so now I can just bring this to the other side. So I find that 0 is equal, well, maybe I bring this to the other side anyway. So if I take sum over all j x times delta ij minus aij times bj, this is equal to 0, because that's precisely this term is just x times bi is just sum over all j x times delta ij times bj, and the other term is this. So this is just, if I take this identity, bring this to the other side, I can also write it like this. But now this obviously holds for all, so this holds for every I. No? So therefore, we can write this down as a matrix. So thus, if I just write this thing here, all of this is the matrix. So let me write where do I want to go? But the first one I certainly don't care about. So if I put M to be the matrix X times delta ij minus aij for I and j going from 1 to n, so n times n matrix like this, then we see this statement here says that the vector b1 to bn lies in the kernel of this matrix. No, that's precisely what this formula says. No, this was for all I. For all j. For all I. Okay, so this is this. So now, the coefficient of this matrix lies in B. But B is a subring of its fraction field. So we can view M as a matrix with coefficients in the fraction field Q of B. And we know if we have a matrix with coefficients in a field, then the kernel is non-zero if and only if the determinant C is 0. No, and the BI obviously are not 0 because they generate, not all 0 because they generate it. So thus the determinant of M is equal to 0, and so this is the monic equation. This is the monic equation. So sum x to the n plus sum I equals 0 to n minus 1 bi x to the n. So this is okay. So this is this shows this, and the last statement is obvious. So here it is: if B satisfies the monic equation, then this is finite. Namely, this is I think it's just clear. So if B satisfies a monic equation B equal to, so what is it, B to the n plus sum I equal 0 to n ai b to the I is equal to 0, then it follows obviously that b to the n is equal to minus sum I equals 0. So it's n minus 1 obviously, n minus 1 ai b to the I. And so any power of b which is bigger or equal to n can be expressed in terms of lower powers. So it follows that if I take a of b, this is just a plus a b plus a equal to. Okay, we already also used this in the algebra course in a similar situation. Okay, so much for this. So this was as much as I wanted to say about K algebras being finite over each other. So now we want to go back to algebraic geometry and say what the finite morphism is and which is defined in terms of this. So definition. x and y be affine varieties, so I said the morphism, now we know what this means, the morphism phi from x to y is defined to be finite if ax is a finite. P star of ay algebra. I mean, clearly, phi star of ay is itself a subalgebra of ax. No? So it's certainly an algebra, and so and it certainly lies in it. So this is the situation. And now, I should maybe remark that in general the definition of finite morphism is more general. One doesn't need that that the varieties are affine. So the general definition, which I'm not going to use, I just write. So remark so 1. In general, a morphism phi from x to y of varieties is called finite if we can somehow reduce to this case, namely if y has an open cover by defined varieties. So this means you have an open cover by subvariety by varieties which are isomorphic to subvarieties of some affine space. Usually you just say an open affine cover, but anyway, such that so maybe I have to actually write y is somehow U1 union K. So maybe it's anyway always finite, right? Which I just say finite open cover. Such that the inverse image phi to the minus 1 of ui in X is also affine for all I. And if I take the morphism and restrict it to here, to its image, it is an affine morphism as before. And I take phi restricted to phi to the minus 1 of ui, or phi to the minus 1 ui to ui is the finite morphism. Of affine varieties. So this is the general definition. So you see that, but we will actually only use this one because but it's one should know that it is something like that. So you see it one very much reduces to the affine case. You have an open affine cover, the inverse image of the affine thing must be affine. And so it's very different from, usually morphisms are not like that. If you take projection from P1 times P1 to P1, it's certainly the inverse image of something is not affine. And okay. So this is the first remark. But we are not going to use this. I just wanted to state it, and so that you know what the definition is. Now I want to have a few examples of finite morphisms, which then we want to use. So a situation where morphism is finite. So the first one is that y in X be a closed. So now X and Y, now we assume we are in a defined situation, so x and y are both defined. I could also find the closed subvariety. So then the inclusion map I, which maps y into x, so basically that's the identity on y, the map from y to x is a finite morphism. And this is obviously in this case, I take I upper star from Ax to Ay is surjective. No, because they just have, this is, this lies in sum n, this lies in semi-n, this is kx1 to xn divided by the ideal of x, this is the thing by y, and the ideal here is bigger, so divide by something more, so we have just put the natural projection. And this one is certainly surjective. This is that's what it is. The it's right. And so then clearly the map is surjective. So what is another case? So and then we want to use this thing that we just proved about how it works with the composition of being finite over something. Obviously, as we have explained what a finite morphism is in terms of an algebra being finite over another, this directly translates. So we have therefore the following result. So let phi from x to y and psi from y to z, the morphisms of defined varieties, so if phi and psi are finite, then it follows that the composition psi composed with phi is finite. This is because it's just a translation. It says here A of this is finite over this, and A of that is finite over that, and so then the composition. And obviously the other statement we had in the same part 1 of this proposition translates in the same way. So if we have psi composed with phi is finite, then the first map is finite. Before we had if one algebra, if we have these three algebras, one over the other, and then if the composition is finite, then the second step must be finite. But now, as we reverse all the errors because we do the pullback, so therefore this one is finite. This is just a translation. So this is clear. This is a translation of proposition. So in particular, one case which we use, so in particular, it's kind of trivial, but we want to, if phi from x to y is a finite morphism of affine varieties, and with the image of x contained in a subvariety W, So closed subvariety. Now, and then we have that if I take phi, and now I view it as a morphism from X to W, this is also finite. Now obviously, if we have by our definition, if you have a morphism from X to Y, which actually maps into a subvariety, we are allowed to view it as a morphism to that subvariety. And now, this statement here is that this is the second part, because we could view this map phi from X to Y, we can view as a composition of the map from phi from X to W composed with the inclusion of W to Y. Phi X to Y equal to phi from X to W. It goes the other round, but anyway. So we have the inclusion composed with phi from X to W. And so if this map was finite, then also the first map is finite. Okay? So these are all trivial things, but it's nice to know that we will need to use this without any hesitation. Okay. So our aim is now that we want to show as next thing, maybe hopefully before the end of the lecture, that if you have a finite morphism, so any finite morphism is closed. So remember that for a morphism to be closed means that the image of any closed subset is closed. So this is, we know that morphisms starting from projective varieties are closed, but usually morphisms starting from affine varieties will be very far from being closed. I mean, there's no reason why they have to be closed, but if they are finite morphisms, they are still closed. Okay, so we first want to remember so we have first a little remark. Maybe I should say that so if maybe I don't know whether I had this notation already, so I first introduce it. So if X in the N is an affine variety, then and say I in A of X is an ideal, I want to write a zero set of I just to be the set of all points P in X such that f of P is equal to 0 for all f in I. So before we had only talked about ideals in the kx1 to xn. But note that C of I is just C of, say, pi to the minus 1 of I, where pi from AX1 to xn to AX, which is kx1 to xn divided by the ideal of x is a natural projection. Now you can see this immediately that the zero set of all these is precisely just this, because we are in x. So Okay, so therefore there's no problem. So I just, but it's kind of nice to be able to think of the zero set of an ideal in the coordinate group instead of, and so now we have the remark that, which is, so let again x in a n variety and E I a proper ideal in A of x then, well, we have basically the Nullstellensatz again, so if we take the zero set of I, this will not be the empty set. And it's clear this is actually just a translation of the usual Nullstellensatz, because we have that after all, z of I is just z of pi to the minus 1 of I for this projection here. And as this was a proper ideal, this is also a proper ideal. So e to the minus 1 of I is strictly contained in kx1 plus n, and so by the Nullstellensatz. The zero set of I is not empty. Okay. So now we want to show that finite morphisms are closed. After this preliminaries. Make first the theorem. So for us, finite morphisms are always finite morphisms of defined varieties, but the theorem would hold without that assumption. But as we only work with defined varieties, we only do it in defined cases. So finite morphisms are closed. So we take a finite morphism with f from x to y, finite morphism. Of defined varieties, and let W x be closed subset. And so we have to show that the image, we have to show f of W in Y is closed. Okay, so that's what we have to do. So let Z be the closure of f of W in Y. So we can take this closure. So then instead we have to show that f of W is equal to Z. And notice, so by what we just say, if we take f restricted to W, you just see, from
consider it to be the composed with the occlusion of f of W.
what?
We can consider f as f from x to fw with the occlusion.
Yeah, no, but we want an affine variety, so we put it to be Z. From F to Z. And this, according to what we said, is a finite morphism. Because we have first the inclusion of V into, so, I mean, this is a finite morphism. Okay. There you can check it. So, and now, with this assumption, we saw obviously clearly f of w is dense in Z. No? And we, because this was supposed to be, so if f restricts to w, so this is dense in Z because that was a closure. So, what we want to show that Z is equal to f of w. So in other words, we have reduced to the following statement. The theorem to the following. So we have that f of x to y, the finite morphism, with f of x dense in y. Then we have to show f is surjective. No, this is just this via this thing we reduce to this case, because we now can put the x, the w becomes the x, and the z becomes the y. And then, so we have to show that. So now we can again gloriously use the homework. So the map is the image is dense, so we know that the pullback map is injective. Yeah. Because of this, I will allow myself to not always write the pullback, just write something H here for the pullback here, unless it confuses you. But anyway, this pullback map is injective. I will see whether I allow myself or not. So I wanted to say identify AY with F star of AY in A. Now we could make certification, or if you wish, you can always keep track of the F star. So now we somehow have to see how we can prove that this stupid map is surjective from this assumption. So, well, we just pick a point in Y, and we have to find that it is in the image. So we assume that Y lies in some fixed AN. No, that was defined. And P equal to A1 to AN is a point in Y. And so let's look at the idea of this point. So what are the functional values there? We just take x1 minus a1 until x then is equal to let m equal to the ideal. So x minus x1 minus a1, xn minus an. Well, I want to actually take the classes here in AY. If you wish, you would. Okay. So denote. I want to now make an idea. So I could say my ax m. So more strictly speaking, it should actually, well, anyway, I write it like this. This is the set of all am, with a is in ax and m is in n. So this here I've used this identification that this lies here. Otherwise, I could also say, so this would be an ideal. This is the ideal generated by M in AX. So maybe I will also be more honest, so it should actually be AX F star M. This is the set of all A F star M, no? With A in AX. So that's what it really is with the ideal generated. So it's not so much gained by making the identification. Maybe I just like this. So what is now? So I want to see that this point P lies in the image. So let me find out what the ideal or something of the inverse image of the point is. If I take f to the minus 1 of P, this is the set of all Q in X, such that f of P, f of Q is equal to P. No? This is the set. Well, how can I check that f of Q is equal to P? It has to satisfy these equations. So that is, this is a set of all Q in X, such that xi minus a I, so this is point P, so if I compose this with F, of P, so I take F, then this gives me a map from X to Y, and then apply Xi minus this to it, and I apply this to F, so this should be equal to 0. So in other words, this is the 0 set of AX F star M. This thing that I wrote here. Okay. So the inverse image of this is the 0 set of this idea. Now by the lemma that we had before, I don't know what was lemma. Yeah, it was lemma. We have that the 0 set of an ideal. So this is an ideal. No, this is an ideal in AX. So this is an ideal in AX. So this thing is non-empty if and only if the ideal is not the whole of AX. So therefore, we have to show, in order to show that it's non-empty, we have to show that this ideal is not equal to AX. So to show f minus 1 is non-empty, which is the same as saying that the map is surjective, and because we have taken an arbitrary point, need to show that z x is strictly concave in AX. I know that AX. So the ideal generated by F star M is smaller than the whole of AX. And so because of this, with this we have reduced ourselves to an algebraic lemma. Note that this M, this is an ideal in here, and clearly it is not equal, no? Because all the elements here vanish at p. So the constant function would not be here. So that's enough to show the following lemma. Is it here? So let P be a finite Lie algebra. And I can assume, again, that B is an integral domain. Let I in A be a proper ideal. Then B times I, which is just this, is a proper ideal. So, what I said, so B is, in our case, is AX. A is F star of AY. And our ideal here, I is M. And then the statement is precisely this. Why can we take this B to be the integral domain? B is A of X, and that X is a variety, so A of X is an integral domain. Okay, so now we have to prove this simple lemma, and this is somehow very similar to what we have already seen, as one can also see from this story again, integral domain, so we are going to use the determinant again in a similar way. So proof. To make it indirect argument, so we assume that it's different, Bi is indeed equal to B. So we know B is a finite A algebra, so we can write B as equal to AB1 plus ABN for some Bi in B. And so now if we look at Bi, so we multiply this by I, everything is commutative, so we can replace A by I. Now we just multiply everything by an element of I, then we land in I, because I is an ideal. So IB1 plus IBN. And so thus we see, and this is equal to B. So we can write B equal to IB1 plus IBN. So we can write B as linear combination of elements in this idea, not just in A. And so we do basically the same thing we did before. So thus we get that Bi can be written as sum j equals 1 to n Aij Ej, where now Aij is an element in I.
Will we prove that B is the zero ring eventually?
No, in this case we won't. I mean, maybe one could, but no, we actually will just prove, we will directly prove that under this assumption, the element 1 lies in I. So it's actually not a contradiction, we do contraposition. So we prove directly that if we assume that Bi is equal to B, then I is equal to A. So now we again write down this matrix, so we put M equal to delta Ij minus AIJ. So the matrix like this. Okay? Then we see this thing says that again B1 to Bn, this vector, lies in the kernel of this matrix. So therefore, again, viewing M as a matrix with coefficients in the fraction field, we can deduce is equal to 0. Because B1 to Bn, obviously, it's not the 0 vector because we have here, it generates the whole thing. So by the formula of the determinant, so by that we had before, we see again we can with one diagonal term, which gives us here 1, 1, 1, 1, 1. So we have 1, and then we have other terms. We get the determinant of M can be written as 1 plus sum over L, we want to call it maybe CL, where CL is an element in I. Because note, these elements are all in I. The only thing not in I is here this delta ij, so we have 1 here. When we write this down, the only thing which does not contain an element in I is, it's not just a multiple of an element in I, is the diagonal thing, and that is, 1 minus A11 minus 1 minus A22 and so on. If you multiply it all out, you get 1 minus or plus something in the ideal. And all the other terms anyway lie in the ideal. So it has this form, and this is equal to 0. And so we see that 1 lies in the ideal. And so, in other words, I is equal to A. And so, in particular, if I is not equal to A, then also B cannot be equal to B. And so that implies that the map is surjective. So under these assumptions, and if one go back all the way, it shows that finite morphism is closed. So now we want to come to the Noether normalization theorem, which will be an important tool for us. As I said, one way to say it is that every affine variety, for every affine variety, you have a finite morphism from this affine variety to a affine space AN of some dimension. And then we will find that the dimension of the affine variety is equal to this number n. And so before doing this, I first have to do some easy preliminaries, and maybe that's more or less how far I will get. So actually, by the way, the other time I mentioned that the Noether normalization theorem was due to the father Max Noether, but I actually was wrong. It's due to Emmy Noether. So that was just, okay. Anyway, she has certainly made more important contributions than him, and although he was a quite well-known mathematician in his time. So, let F in Px1 xn be some non-zero polynomial. It's actually a rather trivial thing, but I just want to say it's something unique. Then there exists a point P in AN, assume with f of P different from 0. In some sense, you know, obviously it's not clear whether one should actually have to prove that. It's kind of totally obvious, but as we explicitly use it in a maybe slightly surprising way, maybe I want to prove it. So proof. So what? If n is equal to 0, this is obvious. No, because the function is either a non-zero constant or it's 0, and so if n is equal to 1, then we can write, we over an algebraic plus 3, we can write f of x equal to x minus e1 to the n1 times x minus en to the er. And as we split into linear factors, and so we can just take so that P in our field case without E1 to be R. Now, as an algebraic recurse is always infinite, we certainly can find this. And now we want to, so then f of P is not 0. And finally, now that n is general,
sorry, but if n is 0, then we just have a field?
we have a field, and f is an element in the field, which is either 0 or non-zero.
Yes, but how? Sorry.
I mean, A0. Maybe one doesn't need it. Anyway. No, but I think we should. We just have the field, and I mean, still, we still somehow need it. I mean, you have a polynomial in 0 variables, which is just a constant, and still it's okay. You know, you need to also deal with the very trivial cases for the induction, otherwise you could have some issues. So, so we can write and f equal to sum I equals 1 to r, say fi x n to the I, where the fi are polynomials in one variable x. No, we just write it like this, just collect the powers of the last variable. So f is non-zero. So we have assumed that f is non-zero. So that means that one of the coefficients must be non-zero. So there exists a j with fj is not the 0 polynomial. So therefore, by induction, there's a point where it doesn't vary.
You mean not 0, right?
Yeah, indeed. Okay, by induction. There exists, say, a1 to an minus 1 in an minus 1 such that fj of a1 to an minus 1 is different from 0. No? Now I can take our original f and put these variables in. So let g of x be equal to f of a1 to an minus 1, comma x is a polynomial in and you can see, okay, this is a non-zero polynomial. No, because the jth coefficients of it is non-zero. So therefore, there is a value for which it is non-zero. So that's there exists an element b in K with g of b is different from 0. No? But obviously this is just f of a1 to an minus 1. So we have found an element, a point where it doesn't go. Okay, that was kind of trivial. And now let me at least state the Napier normalization formula theorem, and then I let you read these. So the following theorem so I think the original Noether normalization would be an algebraic statement. I formulated geometrically. So first, which is actually mostly needed for some kind of reduction step, but we also need it simply later. So let z of f in an be a hypersurface. So it means that f in K x1 to xn is irreducible polynomial. So then there exists a finite surjective morphism check for me phi from the 0 set of f to an minus 1. Okay? So this is a very special case of what we want. Namely, the general case would be that x be an affine variety then there exists a finite surjective morphism. Phi from x to an for some n. Okay. So it actually turns out that the second part is a relatively easy consequence of the first part. So we can use this to do some kind of reduction, and also the statement of the first part will be important to us because it somehow will allow us to say that if we take a variety and we intersect it with an irreducible polynomial like that, and the variety before was not contained in the 0 set of that, then the dimension actually goes down precisely by 1. But that we'll see later. Anyway, so this is the statement. So I don't have, I mean, the proof is a bit, it takes a bit of time, there's no point starting it now, but we'll prove it next time, it's not such a long story. And then we will soon actually properly introduce dimension and apply these things to proof results. Okay. Yeah, thank you very much. I should